Modern networks are anything but simple. Today's networks are a combination of branch and campus locations mixed with on-premises and cloud data centers that are interconnected via third-party access providers, colos, and POPs, leading to several challenges for the operations team, such as observability at scale and knowing what is normal and what is not in this high entropy environment, identifying when there's a problem, especially brownouts, isolating the root cause when there is an issue. Solving these challenges requires three fundamental things. First is telemetry from the network. Second is an intelligent platform with holistic data ingestion. And third is a method of processing the network telemetry in real time that will automatically produce insights for the operator. In this video, we will show examples of how a multinational organization with a global network uses Octera machine learning to detect anomalies in their network, including traffic changes, loss, and jitter, and how they leverage the heat map capability to help them manage these at scale. The example sites are connected using MPLS and internet circuits. Octera is using a combination of data directly from their SD-WAN provider and the Octera NetSonar agent, but it can also ingest customer proprietary probe data. First example is the MPLS circuit. Octera has generated an anomaly due to an increase in packet loss. The context of the anomaly includes details of the circuit, such as the source and destination locations, device name, and interface name. There's a sharp spike in loss on the priority queue. And looking at the timeline, there's no loss prior to the anomaly being detected, which is what you would expect with a more expensive MPLS type circuit. For example, if the circuit had a critical application on it, such as a real-time financial transaction, then even a small amount of loss would be important and the operator would want to know about it. If that was the case, the operator could configure Octera to create a ticket in ServiceNow or another operations tool. The next example is a little more complex. The organization is using the internet to connect from a branch location to an AWS VPC. Internet circuits are unpredictable by nature. Learning what is normal is the first problem, and the second problem is detecting operationally relevant changes from that normal. Octera solves both these problems by uncovering patterns at scale. Here, Octera's correlated anomalies for both RTT and RTT jitter. Using the time series data shows the normal pattern and the anomaly. The third example is a pair of sites connected using the internet. Notice that Octera has correlated anomalies this time on loss, RTT, and jitter. The particular circuit always has some kind of loss on it and is using the best effort queue, so using thresholds for loss will be problematic. The operator is also likely aware that there is some loss in the circuit since it is always happening. With Octera ML, only the anomalies will be reported. To reduce noise, Octera would only create one correlated ticket to the operator that includes the details of each anomaly as opposed to separate tickets for each telemetry type. This is another real traffic anomaly from a production deployment. As we have seen, Octera does anomaly detection on individual interfaces, but will also automatically create aggregate objects based on metadata to monitor groups of interfaces together. In this example, Octera is doing ML on aggregated traffic for all the interfaces connected to the colo. The total traffic has a major increase, and the anomaly is clearly seen when looking at the time series. In fact, Octera has produced several anomalies since the event started, as seen when selecting past anomalies. In the video introduction, we talked about the complexity of networks. Having anomaly data is good, but operators also need to quickly isolate the offending parts of the network and be able to do this at scale. A good way to do this is using Octera heat maps to plot performance and anomaly data. In our example, the heat map vertical axis is the source probe and the horizontal axis is the destination probe. The three heat maps at the top are all related to lost packets and anomalies. The two blue heat maps are the raw data points, and the red is a plot of Octera anomalies on that data. The darker the shade, the higher the value. Hovering over a specific square will display the value, and the operator can even zoom in on a specific area or time. On the red anomaly heat map, you can see there is much less noise with some clear patterns. Specifically, we have two source probes and one destination probe that are jittering most of the anomalies. As you would expect, we can see the correlation between the raw data and the anomaly heat map. Using this view, the operator can quickly focus their attention on the problematic circuits. We are now looking at a different set of heat maps that have to do with round trip time, or RTT. This is a great example of how machine learning cuts down noise. With RTT, we have considerable variance between the different types of circuits. One shows much darker on the raw data heat map, but just because that circuit has a higher RTT does not necessarily mean we have an issue. It may always be high. Looking at the anomaly heat map, we can see we only have 20 RTT related anomalies, and they actually correspond to the same circuits that had the higher loss anomalies, not the ones with the higher RTT time. For this operator, a combination of automatic anomaly detection and heat maps enable them to monitor their multiple networks. They are able to know immediately when their circuits have issues and where in the network it is happening at. Thank you for watching.